Yeah. Gily, Ginosar.
Well,
All right, let's get started. Thanks everyone for coming back for day 3 or final day, and we're going to kick it off with Gily Ginosar talking about 3D geometry of grid cells.
All right, good morning. So my name is Gily Ginosar, and I'm a PhD student in the University lab in Israel. So 3D grid cells in bats. So continuing from yesterday's and Sam's talk, we know today that the spatial memory and navigation happens largely in two highly interconnected areas, the hippocampus and the entorhinal cortex. And here in the hippocampus, this is depicted in our brain, the hippocampus and the entorhinal cortex. In the hippocampus, you can find gray cells. So this is a on the top here. This is a top view of a box where a rat is running around. In black, you can see the trajectory of the rat, and in red, you can see all the places where a single cell fired in that box. And that's also shown in the firing rate map in the bottom. That's in the form of a heat map. So red high firing, blue low firing. So pieces place cells in the hippocampus, and in the entorhinal cortex, specifically in the medial entorhinal cortex, you can find border cells, which are we heard about this also yesterday from Sam, firing at the geometrical borders of an arena. We can find head direction cells, like what Vivek told us about, just firing wherever in specific head direction of the animal. And grid cells. So here's a beautiful example of a grid cell. This was recorded in the Moser's lab. And again, this is a top view of a box. The gray is the trajectory. The black are all the areas where a single cell recorded in the medial entorhinal cortex fired. And you can see this pattern has multiple firing fields, and the most prominent property of this firing pattern is, of course, its hexagonal symmetry. But another, perhaps more low-level property is the characteristic distances that we see between neighboring fields. And what I'm going to argue today is that it's the characteristic distances, that's the property that is maintained in both 2D and then when we go to 3D as well, rather than the hexagonality. All right, so everything we know today about these types of cells comes practically from rodents running around 2D surfaces, but our world is three-dimensional, and mammals live and navigate through 3D space. And so we ask, what would grid cells and the other cells fire? What would be their firing pattern in 3D, and how would the brain represent space in 3D? And so we turn to the flying mammal, the Egyptian fruit bat, and let me tell you what happens in these bats in 2D when they're crawling on surfaces. So the lab has shown that the grid cells in 2D in crawling bats are comparable to the ones seen in rodents, and also the rest of the spatial cells that are found in rodent brain are also found in bats crawling. So we have the play cells, the border cells, and the head direction cells. Also, the lab has shown that in bats flying in 3D, there are 3D play cells, and they are roughly spherical in shape. Now we want to know, what do grid cells look like and what do border cells look like. And for that, we do Tetrode recordings in the bat entorhinal cortex. We use a wireless neurologger mounted on the bat's head, so it's just flying around without any wires connected, and it stores it on board. stores the neural data on board. And the bat flies around in this 5 by 6 meter room, foraging for food. And here in gray is a typical trajectory, and so on a typical day, a typical session, a bat would fly an average of 2 kilometers per session. So they do a lot of flying. So let me just show you. This was recorded in my lab. Show you what it might look like. Do you see anything? Well, there's a bat there. You can see there. You can see in white the eyes, and they're just flying around.
Is that real time or is that slowed down?
No, it's not.
What's the wingspan of a bat?
What's the wingspan?
Size? These ones?
Anyway, so they fly. It's not complete darkness. It's pretty dark, but not complete darkness. They can still see. They use their sonar, but they can still see. So they use both modalities. All right. So so we talked about this. What's happening in the hippocampus and what's in the entorhinal cortex, and so we already know in 3D how clay cells look like in bats and how head direction cells look like in bats. Now we're just left with the border cells and the grid cells, so I'm going to talk about both. Start with the border cells. So in 2D, when rodents run around, a border cell is just fires along the line of the border. So it would be we're in a 2D surface and it fires along a 1D line, right? So what would it be like in 3D? Would the border be a line, or would the border be a surface on the border of the 3D space? So the answer is we see both. So here is an example of what we think is a planar border cell. What you see here is a top view of the room and the 2 side views of the room. In the spikes, you see that when you look at the top view, it's pretty much firing all over, and then you see in the side views, they tend to fire more closely to the floor, and that's also shown in the firing rate map. Another example for this, here you can see it, I think, more clearly in the spikes, just in the raw data. So it's just firing around the floor. So this is what we think looks like what could be a planar border and a linear border. Here we see this is from the top view, firing all over this side. And when you look at it, it's like let's think of it as like a sausage. And when you look at it here from the side, we're like cutting it, and you see something small, putting it up here. And then this is from the other side, and you can see it elongated. So, for example, it would be like it's firing all over this, where the ceiling meets the wall. All right, so here is another example for this. So these are border cells that we see that they're firing along the wall. We see, yes.
So these are the firing patterns when the bats are flying.
Yeah.
When they land on the wall and walk, do they have a consistent?
Here they're not allowed to walk on
Okay.
and we're actually taking only the data of the flight. So we're taking once they take off.
Like if people do check whether there's consistency across context, flying versus walking.
Yeah, we tried to check it, but I'll tell you a little bit about it later.
Okay.
But I'm not going to show data of that. All right. The thing is, okay, I'll get back to it now. The thing is, it was kind of hard for us to get the same cells from bats that are both crawling and flying, because, well, specifically for the grid cells, it's less of a problem in the border cells, but we really need a lot of coverage in both flying and in the crawling, and we need a big enough space to see multiple fields and so on. You'll see the fields in a second, like how big they are. And so getting the bats to do both things and not get exhausted was I'm just going to do it. All right. Here's an interesting example of something a little bit different that we talk about it in the context of border cells. We don't really know what this is, and it looks like a little bit of like a border cell that is firing a little bit away from the wall. So, for example, here, so you see it's like a line, and then when we cut the sausage, it's not exactly on the wall. It's a little bit to the side. So, and here is another example. So when you cut it in the middle, it's not on the border, but it is kind of linear. So we are thinking of this maybe this could be connected to the fact that the bats don't only have the visual information; they also have the sonar information. So they could know at any time the exact distance from the border, even though they're away from it. But if any of you have heard of boundary vector cells, this also might be connected, but we don't really know.
Can I ask a question? I mean, how much of this is driven by vision, as you mentioned, and how much of it is driven by acoustics or the sonar?
That's a good question. I don't know. I think most of it, like I haven't checked it, I think most of it is vision. Like usually they would do, since we're not doing it in complete darkness, and they do use vision naturally, usually they would use the sonar just, when they're taking off, just before like taking off, and then when they're reaching somewhere, or if they're confused or stuff like that. I mean, the continuous, what the information that they use all the time is the vision. So yes.
And I'm going to be talking about later, and also olfaction, because they actually have
Right.
Sorry. And the same thing with the rat data on border cells. I mean, odors actually pool along edges, and so I'm just wondering how much of these this is stimulus driven.
That's a good question. I know that in rodent work they go into like a lot of trouble to clean their arena before and so on.
Yeah.
We don't.
Right. No.
Just
But
like
even,
a naturalistic.
but no matter how much you clean it, whatever odor is there is going to still pool on edges, and like Han Lever's got walls in the middle of the arena that a wall would also trap it. I know. I just pointed that out.
Yeah. That's
I'll
a
be
good-
talking about
that's
that a
good
little
point.
later.
That's a good point. So vision, sonar, and odors. Yeah. Actually. Yeah.
Just thinking, as you say, you're recording not in complete darkness, that's for recording purposes, but
No, also because we're recording in the amount of light that they feel comfortable in. Because also when they fly at night, it's usually not complete darkness, specifically today, with light pollution and the cities and so on. So we recorded, like when they are in complete darkness, then they use a lot of sonar, but they're also kind of stressed.
but that's what I was getting at, that with the degree of light, you could potentially scale how much sonar, how much visual information is being used.
Right. So there was a paper from the lab, I don't know, 2016, where they did like complete darkness and non-complete darkness, and they actually showed that there are different maps. So in the play cell, so in complete darkness, rather than when you use sonar and when you use vision, you have remapping of the play cells. Yeah. All right. So these are things that we think might look like linear borders. Last thing I want to show you here is a little bit of a curiosity, where, in a lack of a better term, we call this anti-border cells, but they would fire in the whole room except for just around the ceiling or just around the floor. And we actually had many of these that are firing all over, like they don't see spatial at all, but they don't fire
along the floor. So if you have a better name, tell me. All right, so this is what we have about 3D borders. So some of them look a little plainer, some of them look cleaner. Becomes like bordering the 3D space. So now I want to go into grid cells. What would grid cells be? Yes.
Of course, in a natural environment, say a cave, is a very different geometric configuration that they
That's
can
true.
sort of evolving in.
Yeah, so you could ask yourself, like, would a border cell be like, where the wall of the
That's the
cave
question.
sees the floor, or would it be just like,
Regions of what-
part of the, yeah. But I agree, it won't be, although many, at least in Israel, many of the bats, like in Tel Aviv, Tel Aviv and the nearby city, Yafo, they live in like abandoned houses sometimes, so there they will have planar border cells.
These are all,
Abandoned houses in Tel Aviv?
What?
Are there-
In Yafo.
these are all adult bats,
These are adult bats,
and
yeah.
is there a sense as to how much plasticity there is? Just continuing along with what you said, juvenile will have the same kind of.
That's a good question. That's actually an ongoing project in the lab now to look at juveniles and how they, but we don't have the answers yet. All right. Question? Yes.
Is there a difference between how much their flight spans the upper parts of the room versus the bottom of the room? Is there a difference in their, so do they avoid the bottom generally, or is it close to
So-
the floor, or is there?
So, that's a good question. I mean, they naturally, they don't really like to get very close to the floor. I mean, if you're down on the floor, if you're not flying and you're down on the floor, then something bad is going to happen, right? Like a predator will come. But what we do, like one of the things that we will have to do in this study is make the setup such that they would cover as much space as possible. So actually, there's the room, and then we have like the food courts around the periphery, and we put it in different heights so that they really have to go down and cross the room. Since it's just in the periphery, they have to cross the room in different. But then I think that the cells that look like border cells are the ones that looks like border cells in the firing rate map, and those are already like compensated for the time. But yeah, you're right. All right. So grid cells. What would grid cells look like in 3D? Let's talk about what grid cells look like in 2D. So what's the geometry? We can talk about the shape of the individual field, and we can talk about then the arrangement of multi-field fields, how they're arranged in space. So in terms of the shape, we know that in grid cells, we see roughly circular fields, and how they're arranged in space. So there's a few properties that I can think of. So there's a narrow distribution of of the distances between nearest neighbors. That's what I showed you before. There are the 60 degrees angles between triplets of neighboring fields. The fields are in fact on the vertices of the lattice. The lattice is hexagonal, and also the hexagonal pattern is the optimal packing of circles in the plane. So now with this list in mind, I can see which of these things are maintained in 3D. So we can think of in the sense of the shape of the single field. We can think that the field might be, for example, cylindrical. In fact, giving us no information about the z-axis, if maybe that's not important. So this could be, this in 3D could give us a grid cell in 2D, or the field of a single shape could be spherical, like what we saw in 3D play cells. And
if it is in fact spherical, then there are all these options of how the fields are arranged in space. So they could be in a global order, like in a lattice arrangement, all the way from being completely disordered in 3D. And it could be anywhere in the middle in terms of order, and for example, have a local order and not a global order. So let me show you the data. This is one of the cells. What you see here is the firing rate map sorry, of a single cell in the 5 by 6 meter room that we saw. And here are 8 different examples. And you can see that all of them have these multiple, roughly spherical maybe, multiple 3D firing fields. So what we do with these is that we detect the ones with stable field, with 10 or more stable fields. And then now we ask, okay, how are these fields arranged? So I'll go to each of the properties that we said before. So 2D, we have the roughly circular fields. And in 3D, is it a cylinder? Is it a spherical field? And so we see that it's roughly spherical. We compare the field size along the X, Y, and Z dimensions of the room. We see that it's not very different, and we say, okay, there's no systematic elongation along any of these room axes.
But if you look carefully, the variance in Z seems to be smaller than X and Y. Is that
That's true.
real?
Well, they're also the room is squished, so it's not. It's so yeah, I think it's real. The room is squished, and then there's less of a.
If you try to do the same, but that's I mean these are adult bats, right? So I mean these cells or these fields are already in place.
They're in place. Yeah.
So if you say
Yeah.
the room is squished, I don't see how that would matter because it's all there already before you move them into the room.
Because I think the room is squished in the sense that there is like less of a I think it would be different if we did it in a complete
Sphere.
no cubic room. But anyways, it doesn't. I mean, I think it's real, but it's not. I mean, for example, here, why do I say I think it's real? I look here and I see. All right, it could like these kind of fields. They do look kind of larger on the XY than on the Z, right? I mean, it looks a little bit squished, like the room does. But what I'm trying to say here is not that it's perfect spheres, but that it's not cylinders, that it's not systematic cylinders.
But this might suggest it's more like a pancake.
It could be a little bit like a pancake, but it's not in all of the cells. Like in here, I do agree that some of them look like pancake, but for example, this one doesn't.
I mean, there's good reason why Z would be different because of gravity, presumably. And
That's true.
And I don't know whether they need high resolution, and therefore they basically have much narrower receptive fields in the vertical
That's
for
true.
resolution.
I can show you later the rest of the cells, and you can tell me if you think it's like a big deal. We didn't think it was a big deal, but especially because we look also at the individual fields, and you see that it doesn't look systematically like a pancake and not like elongated. But I think this comes from the fact that the room is a little bit squished, yeah, and maybe it makes sense to a little bit.
Could you,
Yeah.
could you do a room where you just have one part of the room squished? I mean, to see, like within, if you had an irregular room, with one area was a lower
Yeah.
ceiling with that.
Yeah, I think we could. I think I'm not sure like we're really interested in doing that because like we don't really care about the shape of every field. We were just wondering, is it roughly spherical? We see in many of the cells it is roughly spherical, and you know, they don't really all have the same shape. So some of them are a little bit more pancakey, some of them a little less. So like I don't know if like we don't really care that it's
So they argue that the map is there and maybe the room doesn't matter. It's still okay with this because, right, in real life there's much more span to fly on the XY than on the Z, right? They don't fly to the moon. So it makes sense that it not would be perfect sphere, but rather a little bit narrower on the Z.
Yeah. I think the little bit pancakey, which we see in some of the fields, not all of them, is probably because of the room, of the behavior, and so on.
Are there any experiments where they alter the body of this animal to do that, and does that do anything to these firing patterns?
For the grid cells,
Yeah, in general, in this hippocampus literature, is there any experiments where I seem to notice that everything is kind of thought out about kind of allocentrically, but you have to move anyway, so I can't help but thinking about what's the influences of this feedback that you get from your kind of aesthetically afferents that constantly feeds back to the brain. And I wonder if you were to click the wings or do something that doesn't quite impair completely the flying patterns, but kind of change what happens there. If it's all completely invariant to that. Just curious. If there is no literature, fine. I mean, I'm not familiar with the literature, so I don't know.
well, people did things that are a little bit different from what you're referring. But maybe I'll tell you about it later, and I'll continue.
Yeah, we should like
Right,
keep,
right,
finish
yeah,
our talk.
right,
Yeah.
right.
All right, sorry, we're continuing. All right, so where were we?
Spherical.
No cylinder spheres.
Very good, very good. They're not cylindrical, they're roughly spherical. They're not every one of them is completely spherical. But sometimes this here looks better. And so on. Okay, so we cross out the option of cylindrical and we can go on. Now we go to the characteristic distance between neighboring fields. Okay, we saw that happens in 2D. What happens in 3D? Is that also the case in 3D? The way we look at this is we compute the distance between each field and its 3 neighboring fields. We do that to each of the fields. And here I plot the distribution of the distances of neighboring fields for this example cell. And you can see that the distribution is pretty narrow, suggesting that there is a characteristic distance in this cell. Now to quantify it, we compute the coefficient of variation of this distribution to see how fixed it is, how fixed the distance is. And for this cell, it's significantly lower than that of 1,000 shuffles, where we just take the spikes, we rigidly shuffle them, move them in time. And so we have this narrow distribution of distances, suggesting that there is a local order here. So something is ordered here in these cells, and out of the cells that had enough multiple fields, 20% of them were significant, had this narrowly distributed distances, having a local order, and these are the cells that we think of as the 3D parallels of or equivalents of grid cells, because they have the characteristic distance that we see in 2D grid cells. Just one second. And so for these cells, we can say that since we have this local order in the fields, we can now cross out the option of their fields being just randomly arranged in space. Was there a question?
Yeah, I was just wondering, so the cells you're recording from, you don't have data for the same cells, just if they're 2D grid cells, for instance, so you don't have that, right? Or,
Right.
Okay.
We couldn't have the same cell. Well, that's, yeah. All right. So now you can say, okay, you see this local order, but maybe there's also a global order to these fields. For example, hexagonal lattice, and the main suspects of a hexagonal lattice, of a 3D hexagonal lattice, are two options. It's called FCC, it's face-centered cubic, and HCP, hexagonal closed vector. They're two lattices of 3D hexagonal lattices. And what you need to know about them for now is that they're also the optimal way to pack spheres in 3D. And several theoretical papers suggested that 3D grid cells would look like either FCC or HCP. So I won't go into details now, but we just did exhaustive comparisons to all possible FCC and HCP lattices. We simulated them like around 3 million combinations of all spacing, 3D shifts, and 3D rotations. And we found that none of our cells, none of our neurons showed an FCC or an HCP arrangement. And we can now cross out this option of a hexagonal lattice, the fields being arranged in a hexagonal lattice. But now you can say, okay, maybe it's not arranged in a hexagonal lattice, but maybe the property that's being conserved is being a lattice. So for example, a different lattice, a cubic lattice, just as an example. So what's a lattice? When we have a lattice, we'll have, if it was a hexagonal lattice, we'll have a bias of 60-degree local angles. If it was a cubic lattice, just as an example, we'll have a bias of 90 degrees. So what I do is I compute the local angles between triplets of neighboring fields, and we see no such bias in the angles. So this is for the ones that we marked as the grid cells, and these are the rest of the cells with the multiple fields. And the distribution of local angles is just as similar to that of the shuffle data in black. So we now crossed, and we have no fixed angles, and we can now cross out the option of the cells being arranged in just a different, any type of lattice. And so now you can ask, how could it be that it's
Sorry. Models like the ones that Sam showed yesterday usually assume that you form some kind of lattice at the level of the network. Then you integrate proprioceptive and sensory inputs. You integrate proprioceptive and sensory inputs. If this integration is not perfect, then you wouldn't see a lattice at the level of the single cells. So do you have pairs of simultaneously recorded cells where you can look at correlations and see if there is structure there?
That's what we're doing now. Yeah, that's what we're doing now, and that could answer both these kind of questions and like manifold kind of questions. So exactly. But I still don't have it to show, but that's like our next step. All right. So you could ask, how could it be that we have fixed distances, like the characteristic distance, but no global lattice? And the answer here is because we don't have these fixed angles. So I'll just give you a quick intuition in 2D. So here is a perfect global lattice. I take the unit and I translated it, and it looks exactly the same. And here there's a local order, but there's no global lattice. We take the unit, we move it, but then it needs to rotate in order to fit. So here, fixed distances, but no global lattice. All right, so what we know now is that we are somewhere in the middle, not completely random, not a complete lattice, and we have a local order. Just one more thing I want to tell you about this is that, and we'll do it quickly, that we know in rodent work that grid cells, the characteristic distance increases when you record, the deeper you record from dorsal to ventral MEC, the medial entorhinal cortex, and we see the same thing in our cells.
So this is the deeper you report from dorso-ventral. This is the interfield distance, and it increases. And the interesting thing here is that it happens to both the grid cells and the rest of the multi-field cells. And in fact, we think that it's there's the grid cells and the rest of the multi-field cells kind of form a continuum. We don't think it's really different like animals, right? So we look at the rest of the properties, so field size, number of fields, the distance itself, and so on, and they're all continuous. Maybe I'm like running really behind.
Yeah, let's hold all the questions until the end. Yeah.
All right, so now we wanted to model this, to have an understanding of how we could have this local order without a global order. And well, this is work done with Jonathan El-Khadef, Yoram Burak, and Chaim Sampolinsky. And so what we know is that many physical systems placed in different parameter regimes can be arranged either as a lattice or a less ordered structures. And these systems are often described using pairwise interactions between particles. So inspired by that, we used a common model that's used in systems with multiple particles, the Leonard-Jones potential, which just means that fields, so we don't do particles here, we do the fields, and the fields close by repel each other, fields farther away attract each other, and then fields until they find this equilibrium distance between one another. And we also introduce noise to the model, which just means how much a field is allowed to deviate from its equilibrium position. And using this model, we see that when we compare the distances between all pairs of fields, our model explains the data much better than when we simulate fields randomly arranged in the room using random Poisson. And so this is in 3D. Our model explains the data better in 3D, but now we want to know how I'll ask me later. Now we want to know how are the fields actually, are they very ordered? How are they arranged? So for that, so we can't use the gridness score. For those of you who know that gridness score is defined in 2D. So what we use here is the radial distribution function, which just means the density of the fields as a function of the radius. And we can do that in 3 dimensions. So, for example, when we look at the radius of the closest neighbor, right? So we'll have a peak in density because we have these characteristic distance between neighboring fields, but only if we're looking at a very ordered structure, we'll have another peak in the radius of the second nearest neighbor. And so this is what we use to quantify it. And in fact, when we do the simulations in the room, we don't get this second peak. So we get the first peak because we have the characteristic distance in 3D in the simulations as well, like we have in the data, but we don't get the second peak. It's not highly ordered. But now we do the same simulations in 2D. When I say 2D, I mean that we do it in a very squished room in the height of like 10 centimeters, so we have only room for around one layer of spheres. We do the simulations in 2D, and there, using the exact same potential, same model, we do get a second peak. So when we do it when it's confined to 2D, it is organized in a more structured way. And now, the surprise here is that not only it has a second peak, not only it's organized, but many of the simulations come out that they have a high gridness score, so they're arranged in a hexagonal pattern with this pairwise interaction between the fields and
well, these are the 4 best examples, but many of the, so you see the grid score is kind of skewed to hybrid scores. And so many of them come out highly ordered and also hexagonal pattern. Yes.
That's relation, for example.
But this is relation.
But in Edward Jones, okay, you have the packing ratio parameter. If you pack enough spheres in 3D, it also should get some, depending on your temperature, get some grid. No, isn't that?
Right, but here we match the number of fields that we have in the data.
I see. So that comes from
Yeah.
data.
All right. So, what should be the take-home messages? The first one is that we see 3D grid cells, and they have, because they have this local, they have multiple fields first of all, and then they have this local distance scale that we see between the fields. However, they do not have the global lattice, the global arrangement. And also, we find out that the common property in grid cells, what's conserved in both 2D and in 3D, is this characteristic distance rather than the hexagonality. We have a model that in 3D yields only local structure but not global structure, and in 2D in fact yields a global hexagonal lattice using the same model. All right, so this is work done in the lab of Nahum and with our collaborators, Chaim Sapolinsky, Yoram Buak, and Jonathan Chadev. And thank you. Yes.
We're probably not going to be able to do all of these questions.
So
a few of them.
usually,
No, don't let them ask all.
so usually in statistical physics, it's hard to get the order in 2 dimensions, and it's easier for something to have order in 3 dimensions. And it's the other way around. I guess just a comment.
Right. I don't know how to answer that other than, I mean, in the 3 view, there's like more degrees of freedom, right? And you could also think of it like we haven't modeled this in this way, but you can also think of it even if there wasn't, in Leonard-Jones, there's the attraction and the repulsion, right? I mean, and then that creates like the distance. But even if we didn't think of it as an attraction and repulsion, even if we thought of it as like a hard sphere problem, where you just pack, like someone said, like where you just pack the spheres, then even then it's easier to get an ordered organization in 2D than in 3D. So for example, in 3D, there are all these things where you can do you pack spheres and then you kind of shake it down and you can get stuck in the local minimum of jam packing rather than like a global packing. So I think that could make sense in more than one framework, but I don't know how to.
Sure, take one more question.
Yeah, okay. Would you have any guesses as to the functional implications for your particular patterns that you hypothesized versus what you found? And related to that, would you expect that, say, for certain bats with, let's say, a pronounced organization, that they would be better in their accuracy of, say, arriving at a target, so that, let's say, the pronouncedness in one bat versus another one is actually then or gives rise to their accurate targeting of a prey. But two questions.
Yeah. As for the function, what could be interesting is that maybe, I mean, we used to think of grid cells as either being used for position, you know, you can get your position from it, or path integration, sorry. And
Okay, you do it. And maybe this work can say something about, for example, position coding, because many of the models for position coding really need the repetition to work. So maybe we either this could be used for position coding, but then the models need to be a little bit tweaked, or we need to understand how to change them. Or perhaps if you have the fixed distances, maybe it could be used for distance coding. So these are thoughts that we've been having. As for would a bat having a better organization be better at orienting, it's hard to say. Like it goes back to the question: what do these grid cells even do? So maybe we'll find that, and then we'll see. But I honestly don't have an answer. Like it's hard also to assess like the navigational abilities of a bat in that way. All right.
All right, let's thank Gily again. And next up we have Sandra Romano.